Many people often attribute strange weather patterns simply to the whims of Mother Nature or the immediate effects of human activities. However, the reality of Earth's climate is a complex symphony conducted by various natural processes that operate over scales of time and space that are often beyond human perception. Our planet's climate is influenced by a tapestry of astronomical cycles, atmospheric phenomena, and geophysical events that intertwine to produce the weather we experience daily. Understanding Earth's climate goes beyond recognizing the rise in global temperatures or the increase in extreme weather events. These mechanisms include the gravitational pulls of celestial bodies, the ebb and flow of ocean currents, and the shifting patterns of winds high above the Earth's surface. This essay aims to explore some of the less discussed yet crucial factors affecting Earth's climate, such as Milankovitch cycles, Earth's axial tilt, ENSO effects, and the roles of the polar vortex and jet streams. By understanding these elements, we can appreciate the depth of natural influences that shape our climate. Milankovitch cycles are long-term changes in Earth's orbit around the Sun that significantly impact our climate over thousands of years. These cycles include variations in Earth's eccentricity, axial tilt, and precession. Each of these aspects contributes uniquely to the distribution and intensity of sunlight reaching different parts of our planet, thereby influencing long-term weather patterns. For instance, variations in eccentricity, how elliptical Earth's orbit is, alter the distance from Earth to the Sun, influencing the solar energy Earth receives. The axial tilt of Earth, another component of Milankovitch cycles, affects the severity of seasons. The precession of Earth's axis, which is the gradual wobble in Earth's spin axis, also plays a crucial role in modulating climatic patterns over millennia by altering the timing of the seasons. These astronomical cycles are critical in understanding past climate events, such as ice ages and interglacial periods. The angle of Earth's axial tilt, currently about 23.5 degrees, is a pivotal factor in determining the climatic patterns across the planet. This tilt causes solar radiation to be unevenly distributed across Earth's surface, leading to the formation of different climate zones from the equator to the poles. As Earth orbits the Sun, the tilt also results in the cyclical nature of seasons. During part of the year, the northern hemisphere tilts toward the Sun, receiving more direct sunlight and thus experiencing summer. Conversely, during the same period, the southern hemisphere receives less direct sunlight, marking the winter season. This dynamic not only affects temperatures but also influences atmospheric circulation patterns and precipitation. In contrast, regions closer to the poles undergo dramatic changes in weather patterns due to significant variations in solar radiation. These changes in tilt alter the intensity and distribution of sunlight, particularly at higher latitudes, which can either promote or melt large ice sheets, thereby drastically altering global climate patterns. The El Niño Southern Oscillation, ENSO, is a periodic fluctuation in sea surface temperatures and atmospheric pressures in the Pacific Ocean. This phenomenon alternates between two phases, El Niño and La Niña. El Niño occurs when warm water from the western Pacific Ocean flows eastward, leading to increased sea surface temperatures and altered weather patterns across the globe. In contrast, La Niña is characterized by unusually cold ocean temperatures in the equatorial Pacific, which also impacts global weather patterns, but in different ways. El Niño events can lead to significant weather disruptions, including increased rainfall in the southern United States and Peru, which often causes flooding and drought in the western Pacific and southern Africa. Understanding ENSO is crucial for predicting and managing weather-related disasters. The polar vortex and jet streams are significant atmospheric phenomena that influence weather patterns across the northern hemisphere. The polar vortex is a large area of low pressure and cold air surrounding both of the Earth's poles. Although it always exists near the poles, its strength and position change with the seasons. During winter, the polar vortex at the North Pole expands, sending cold air southward across the United States and Europe, often resulting in severe winter weather. Jet streams, on the other hand, are relatively narrow bands of strong wind in the upper levels of the atmosphere. These winds are generated by the temperature contrast between the polar and tropical air. Jet streams play a crucial role in determining the path of weather systems and their associated precipitation. The dynamics of the polar vortex and jet streams are vital for meteorologists to understand in order to predict short-term weather patterns. Solar and lunar cycles also play roles in modulating Earth's climate, though their impacts are often subtler compared to other factors. The solar cycle, approximately 11 years long, involves changes in the sun's magnetic field and sunspot activity. During periods of high sunspot activity, the sun emits slightly more solar energy, which can influence Earth's climate. The lunar impact on climate is less direct but still significant, particularly in its influence on ocean tides. Tidal forces resulting from the gravitational pull of the moon contribute to ocean currents, which are crucial for distributing heat across the globe. These currents play a key role in regulating weather patterns and, consequently, climate. For example, the Gulf Stream transports warm water from the Gulf of Mexico northward across the Atlantic, significantly warming the northern hemisphere climates. Understanding these celestial influences helps provide a fuller picture of the mechanisms driving our climate, which is essential for accurate climate modeling and forecasting. While natural phenomena play a critical role in shaping Earth's climate, human activities have become increasingly significant in influencing climatic conditions. The release of greenhouse gases, primarily through burning fossil fuels and deforestation, has led to a rapid increase in Earth's average temperatures, a phenomenon commonly known as global warming. This human-induced change is superimposed on the natural climatic cycles, complicating the patterns and intensities of weather events. The consequences of this shift are profound, affecting not just temperatures but also altering precipitation patterns, increasing the frequency of extreme weather events and causing sea levels to rise. These changes have severe implications for biodiversity, agriculture, freshwater supplies, and human health. For instance, increased global temperatures can lead to the expansion of deserts and reduce water availability, severely impacting food production and water resources. Addressing these human impacts requires a dual approach. This knowledge must inform global policies aimed at reducing greenhouse gas emissions and mitigating climate change impacts. Understanding the myriad factors that influence Earth's climate is not just an academic exercise, it is a necessity for survival in an era of rapid environmental change. The natural cycles and phenomena discussed herein, Milankovitch cycles, Earth's axial tilt, ENSO, the polar vortex, jet streams, and celestial influences, demonstrate the complexity and interconnectedness of our climate system. These natural mechanisms have shaped the Earth's climate over millennia and continue to play fundamental roles today. However, as significant as these natural factors are, the human impact on climate is now equally pivotal. It is crucial that we not only continue to explore and understand these natural processes, but also take decisive and collective action to mitigate our impact on the planet. This requires global cooperation and a commitment to sustainable practices and technologies. We owe it to ourselves and future generations to maintain a balanced climate and a healthy planet.